My project is decoding hand movements from EEG signals. My name is Riddhi Bhashkar, and my mentor is Mr. Omar Tawakkol. In the U.S., about 5.4 million people live with paralysis. That's about 1.6% of the population, which is a lot. And there are around 18,000 new cases of spinal cord injury every year. And a huge result of this is loss of hand movement. Brain-computer interfaces can fix this by building a new control pathway from the brain. There are many different types of BCIs. For example, electrocorticography BCIs and intracortical microelectrode arrays. And both of these are powerful BCIs but require surgery. EEG is a non-invasive and affordable BCI, which is why it's the most commonly used. The trade-off is low signal-to-noise ratios, though. The brain rhythms are tiny and get mixed with muscle and environmental noise, which is why one of the main focuses is to extract the right features so the data helps us understand control. There's been a lot of success with BCIs. For example, in Aji Boye's 2017 paper, invasive systems restored reaching and grasping in people with tetraplegia, which is when there's paralysis in all four limbs. With EEG, recent work shows that there's been 70% plus accuracy for motor imagery in controlled settings, but real-time accuracy and generalization across subjects is still tough. We're trying to build a practical and reproducible system. So we're using the publicly available PhysioNet EEG motor movement / imagery dataset. And we will implement pre-processing to remove noise and extract features such as band power, short time Fourier transform, and common spatial patterns, and input these into classifiers made with either logistic regression or random forest. And then we'll evaluate the accuracy of these and discuss limitations for real-world BCIs. So the PhysioNet dataset has 109 participants and collects 14 runs of 64-channel EEG data via the BCI 2000. There are two baseline runs, which has the participant with their eyes opened and then closed, and then there are 4 motor tasks repeated 3 times. So in task 1, there's either a target on the left of the screen or the right of the screen, and if it's on, and depending on what side it's on, the participant opens the fist corresponding to that side. And then for task 2, there's also a target that appears on the left or the right, but this time instead of opening the corresponding fist, the participant imagines opening and closing it. And then for task 3, there's a target that appears on the top of the screen or the bottom of the screen, and depending on if it's up or down, like if it's up, then the participant opens and closes their hands, and if it's down, then they curl their feet. And then for task 4, it's also up or down, except instead of actually curling their hands and feet, they imagine it. And so for feature extraction, because EEG is noisy, we have to filter it through pre-processing, and one of the ways to do this is to use a low-pass filter, which lets low frequencies through and blocks the highs, or you can use a lot of filters. Like there's also a high-pass filter, which does the opposite and lets high frequencies through, or a band-pass filter, which only lets a specific range, like for example, 8 to 12 hertz through. And there are 3 features which we can use to find out which movement the signals are related to. Band power, time frequency via the short time Fourier transform, or common spatial patterns, which we will go into more depth now. So for band power, we measure how strong the brain's waves are in a certain in certain speed ranges, like mu or beta waves, and then we chop the EEG into pieces and use Welch's method to see how much energy is at each frequency, and then add up the energy in the range we care about. Basically, band power means we integrate the energy of the signal between two frequencies. For example, from 8 hertz to 12 hertz for the alpha band, or 13 to 30 hertz for the beta band. Different brain tasks like imagining left vs right hand movement change these power levels. Looking at how much mu or beta power changes makes it easier for the computer to tell tasks apart. Scientists already found that beta and alpha power are especially useful for motor imagery tasks. And then for short time Fourier transform, EEG signals change quickly over time because they aren't steady. And that's why we can use the short time Fourier transform, or STFT. So basically, we take small time windows of the EEG, and then for each window, we compute the frequencies inside, and this gives a picture of how the signal energy changes over both time and frequency. You can think of it like making a movie of the brain's rhythms instead of just one snapshot. And finally, these time frequency maps, called spectrograms, can be summarized with numbers or even used as images for deep learning models like CNNs. And then CSP, or common spatial patterns, is a way to find the best combinations of EEG channels that show the clearest difference between two tasks. The goal is to the goal of CSP is to look for CSP looks for a set of filters that make the brain signal strong for one task and weak for another. Once we apply these filters, we get new signals where the differences between left hand and right hand imagery are much easier to see. And basically, these equations are just the math CSP uses to find filters that make the signal variance large for one class and small for the other. So the two tasks are easier to separate. So once we're done with feature extraction, like using band power, STFT, or CSP, we need a classifier to find out which signal means what movement. If the features are already pretty clean and separable, I think CSP strongly highlights the difference between the two tasks. And if it does, then logistic regression is enough. It's because if it's very clearly defined, it doesn't need to be too complicated. But if EEG signals are and usually they're messy, so in those cases, a more flexible model like random forest is better, because it can capture more complex patterns. So the choice depends on the data. Currently, we were originally trying to use EEG Lab, but then we ran into problems importing event timestamps correctly, and because of that, we switched to MATLAB, which we're using to write code right now. We're working on writing code to use the EEG data and plot it and align it with the event timestamps, because we weren't able to do that with EEG Lab because we didn't know how to our files it was just not. It was too hard for us to import them into EEG lab. So right now we're working on that. Oh yeah. Thank you for listening.